having so many people attending my presentation. Well, it was a bit dealing with microscopic stuff. Now we are going back to microscopic, so to macroscopic. The work I've been doing here is a collaboration between three institutions, Gradesens, Omnisens, and a company in Peru called Hunt LNG. And we are dealing with sensing in optical fibers. So I'll start by a quick introduction, giving you some of the context of the work, just to understand why we have been doing that. And then we will go back to a bit of the physics of distributed sensing. Being a physicist, optical scientist, I cannot resist the pleasure to talk about it directly. We will then go over some physics related to the soil atmosphere thermal interaction, because it's really the technique, the approach is grounded in this interaction. And we will see how this has been implemented to the monitoring of the Peru LNG pipeline, which is a natural gas transport system. And why? Just to monitor erosion, localize erosion, detect erosion, and let's say quantify the level of soil we still have on top of the fiber and the pipeline. And well, that's a bit a goodie, because some goodies we got from the analysis. This is something we didn't expect, and analyzing data from 10 years of monitoring, we started to see very interesting behavior. So that's why we believe that we have seen one of the episodes of the El Niño. And of course, that will lead us to the conclusion. So the Peru LNG pipeline is a natural gas transport system, bringing natural gas from the Amazonian basin in the jungle, crossing the Andes to the coast of Peru. And it runs parallel to another pipeline called TGP. You have, let's say, both customers of the same company, Omnisens, and using the same technology. What is interesting is that the Peru LNG pipeline has, let's say, two challenging regions for the operation. So the Sierra region, it's where the pipeline starts climbing the Andes, the oriental slopes of the Andes, and it's a very unstable region subjected to landslides, hydraulic erosion, and so on. And the other section that is of interest is the coast of Peru, where it's, if you have been to Peru, it's a desert, and you have dunes, sand dunes that are moving because of wind, and also you have aeolian erosion, which uncover the pipeline in some cases. So the interesting thing is that, oops, too fast. The interesting thing is that actually the pipeline has an optical fiber for communication laid along its length. And what is important to know is that actually everybody knows the use of optical fiber for telecommunication, but actually you can also use optical fibers to perform sensing operation monitoring. In the present case, it has been implemented for landslide monitoring, erosion detection, and also leakage detection, using strain monitoring for landslide and temperature for leakage and erosion. Now, this is possible thanks to a physical phenomenon known as scattering. You all know about that. And what is interesting is that actually we are trying to catch information from the inhomogeneities, and the scattering is caused by inhomogeneities. It can be from frozen local inhomogeneities, but also moving homogeneities in the fiber, which is which are the well-known acoustic phonons. So, taking advantage of scattering, we have, or there is today instrumentation called an interrogator, with which you send an optical pulse into the fiber, and all along the fiber you have scattering. A fraction of the light of the scattered light is coming back and analyzed and by extracting the information, so the time of flight of the pulse back and forth, we can get information about the localization of an event or a problem. And then there is something more we can do. We can do for each pulse coming back, we can do a spectral analysis. And from the spectral analysis, we can find several lines coming from the scattering. One is the relay scattering, which is at the same wavelength as the input signal. And then you have another one that is very close, called Brillant, which is cross-sensitive to strain and temperature. Actually, we are monitoring the change in wavelength or optical frequency, and that change in optical frequency is proportional to strain and temperature. So combining the time of flight information for each position, the spectral analysis, we can profile either strain or temperature or both. And that's, let's say, that's the type of technique called distributed temperature and strain sensing. An example an example of a temperature profile. So it's temperature versus distance is shown here. We see that we have variation, a certain thickness to the curve. But what is interesting to see here is that we have a variation over the distance that is just the opposite of the altimetric profile. So that's an indication that the optical fiber measured by that kind of technology can be an environmental sensor. And it can give you information about what's outside or on the surface. Now, if we look into the time evolution of the temperature, on the left side, we have an example of the temperature evolution at two positions, the green and the red curve. On the green curve, we have a fiber that is most likely more than 1 meter deep, or buried more than 1 meter deep, maybe 2, 3. And we have a red one, the red one, which is less than 50 centimeters. And if we, let's say, compare the time evolution with the ambient temperature measured in a meteorological station nearby, we see that actually for the red curve, there is a decrease in amplitude and a shift in, there is a time lag, let's say, a shift in time of phase difference. So we have indication that if we can catch variation in time of the temperature with the fiber, that means that, well, the soil on top of the fiber and hence on top of the pipeline is reducing. Now, on the other hand, on the right side, we have an example of a measurement lasting from 2010, when the system started its operation, until 2019, end of 2019. And we see a periodic evolution. The periodic evolution is 1 year, 365 days. And we see that also there is a kind of increase and decrease. We will talk about that later. But what is interesting is that based on that information, and we compare the data with also a numerical simulation or an analysis using the equation, the diffusion equation, we were able to understand that really being able to catch this temperature variation for a fiber that's in the ground, we might be able not only to detect erosion, to localize erosion because we have the position, but also we can maybe estimate what is the remaining soil on top of the fiber. In the pipeline community, they call it the depth of cover. In let's say in the power cable community, they call it the depth of burial. It means the same. So here we have the idea to catch we know that we have a change. We have a phase difference, a time lag, and a change in amplitude. So by calculating the correlation between the ambient temperature with the soil temperature, the measured soil temperature, we might be able to extract that information. And actually, that's what we have been able to perform, and doing some calculation, getting this two relationships for the relationship between the depth of cover and the time lag, and the depth of cover and the amplitude variation. So that's nice. I like the correlation equation. It's an old friend for me. But what is more important is the reality of, or the real application. So in the sand dune area, what we have seen during a pilot campaign, in that specific section over a few hundred meters, we started seeing variation over time at 3 spots. So this is a profile, and we are seeing temperature variation, and the temperature variation changes in amplitude, and changes depending on the position, and changes with the timeline. So this is this is related to the curve we have seen in one of the previous slides. And by calculating the autocorrelation, the cross correlation, we get actually the signal or the information for the 3 positions. So we are profiling that information, and we can recalculate then the depth of cover for each position. So the operator knows that from there, he has to take an action or not to recover the pipeline if he doesn't want the pipeline to be fully exposed. Now, the goodies. And this is something that we have observed. We decided to analyze the data from 2010, and started to see that, okay, we have a drift of the annual temperature change, a drift up, and then a drift down. I was really puzzled because I didn't expect to have that. And it was only at several locations, not the whole pipeline that we are monitoring, but let's say a few hundred meters here, a few hundred meters there. So depending really on the depth of the depth of cover of the optical fiber. So I started to look into the literature and in the famous El Niño, and I started to see that they had a kind of let's say an intense event in 2014, between 2014 and 2016. So I put the curve together, and it was somehow, I'm not saying matching, but there was some kind of, we could establish kind of a relationship between the two behavior. So this is why we are really believing that there is somehow a relationship between what we observed, what we measured, and the El Niño behavior. So now I'm collecting the data to see what's going on with the occurrence, this year occurrence, and maybe next year or in 2 years from now, I'll come and say, oh yeah, I was right or I was wrong. Okay, good. Now, what I presented is a bit of technique, and that allows unattended and real-time measurements using telecommunication optical fibers. For strength sensing, we just add a special cable, but it's connected to the optical fiber. We can detect localize events like erosion. We can quantify the erosion, and it's really helpful for the operator because you can reduce the time between 2 maintenance, because they do that a bit blindly. Here, they can do that. They can schedule for it based on what is observed, and also that allows the pipeline to, that avoids possible breakage of the pipeline or exposures that can lead to a leak. And let's say this is the kind of information that can be really useful for let's say infrastructure owner, because that applies to pipeline, but that can apply to railways, that can apply to highways and so on. Any linear infrastructure that has an optical fiber laid in parallel. So, ladies and gentlemen, thank you very much for your attention.